So this video is a brief description of work and energy. So energy is an important concept that is heavily used in everyday life. So everything around us, including ourselves, needs energy to function. And also everything is made up of energy, okay? So for example, electricity provides home appliances with the energy they require, and food gives us energy to survive, and the sun provides Earth with the energy needed for the existence of life. So experiments show that energy is a scalar quantity related to the state of an object, and it may exist in various forms, such as mechanical, chemical, gravitational, electromagnetic, nuclear, and thermal, okay? And also, it cannot be created or destroyed. So energy can only be transformed from one form to the other. For example, if energy were to be exchanged between objects inside the system, then the total amount of energy, the sum of all forms of energy in the system, will remain constant, okay? So a transformation of energy occurs due to the action of a force known as work, or due to heat exchange between objects or between an object and its environment. And in the case energy is transferred due to work, then it may be defined as the capacity of doing work, okay? So in these videos of mechanics, we are concerned with mechanical energy, which involves kinetic energy that is associated with the object's motion, and potential energy associated with the position of the object in space. So work can have many meanings. So sometimes it refers to physical or mental work, but in physics, the definition of work is different. So work is said to be done if a force is applied to an object while it is moving. So if there is no net displacement, then no work is done. So suppose that a person is holding a heavy box for some time and then starts to feel tired. So the reason the person feels tired is because the chemical energy in the body is converted to internal microscopic motions of the muscles so that he is able to carry the box, okay? But this energy is not transferred to the box being carried because the net displacement of the box is zero. It did not move. So the work done on the box is equal to zero. So now consider an object exposed to a constant force. So if the object is displaced through a displacement S, then the work done on the object is a scalar quantity defined as Fs cosine theta, and this is the dot product between the two vectors, the force and displacement. So theta here is the smaller angle between F and S. So the component of F in the direction of S, which is F cosine theta, is the only effective component that produces motion, okay? So the work done represents energy transferred to or from the object via that force. So if the force is in the same direction as the displacement and theta is equal to zero, then the work done on the object is positive and energy is transferred to the object, okay? And if theta is equal to 180 degrees, then the force is opposite to the displacement and the work is negative and energy is transferred from the object. And the SI units of work is the joule. So 1 joule is equal to 1 newtons times 1 meter. So it's equal to kilogram times meter square over second square. And note here that energy and work have the same units. So now consider an object exposed to several forces. Then the work done by all of these forces is the sum of the individual amount of work done by each force. So this equation can be written in this form as sigma F dot S. So as an example, let's consider an 80 kilogram block that is pulled on a horizontal rough surface, so there is friction by a force of 400 Newton that is at an angle of 20 degrees to the horizontal. So the displacement of the block is 6 meters and the opposing force of friction is 180 Newton. So the work done by the applied force is equal to F dot S is equal to Fs cosine theta, and it gives 2255.3 joules. And the work done by friction is equal to the frictional force times the displacement times cosine the angle between them. So the frictional force is opposite to the displacement, and so the work is negative, okay? Which means that energy is taken away from the object due to friction. And because the normal force and the force of gravity are normal or perpendicular to the displacement, then the work done by both is equal to zero because the angle is 90 degrees, okay? So the total work done on the block is equal to the sum of the work done by the applied force and the work done by the frictional force, and this gives this value. So now let's consider this example where a delivery man wants to push a crate up a ramp, and the length of the ramp is S, okay? And we want to find the minimum work the man must do to lift the crate to the top of the ramp. So the minimum force would be equal to this component of gravity, and in that case, the crate would move with a constant velocity, okay? So the work done by gravity is equal to, by this component is minus mg sine theta times s. And so the minimum work the delivery man must do will be equal to plus mg sine theta times s. So previously we considered the work done in the special case of a force that is constant in both magnitude and direction, and the object moved along a straight line. But in many situations, the force may vary in magnitude or in direction or in both, and the object may move along a curved path. So to find the work done in this case, let's consider a particle moving along this curved path. And while it is moving, there is a force F that is acting on it, and that varies in both magnitude and direction with the position of the particle. So now let's divide the path into a large number of very small displacements. Each is delta Ri. Then the force can be approximated to be constant in both magnitude and direction for each displacement, okay? So for the displacement delta R1, we have F1, and for delta Rn, we have Fn. And so the total work done as the particle moves from P to Q is the sum of the individual amounts of work done along each displacement. So it is equal to this sum. And by dividing the path into more displacements, we have the limit when delta Ri goes to 0, and this is equal to the integration from P to Q of f dot dr. So this type of integral is known as a line integral, and each component of f, which is fx, fy, and fz, may be a function of x, y, and z. And the curve can be determined by its equations that relates x, y, and z to each other, okay? So the component form of this equation can be written in this way. So now consider the case in which the particle moves along a straight line. And let's consider it to be the positive x-axis. And let's suppose that the force acting on the particle has a constant direction along the x-axis, but its magnitude is varying with x. Then in that case, we can write this equation here as the integration from x initial to final of the force, which is a function of position times dx. So this equation represents the area under this curve, okay? So let's suppose that f is constant in magnitude. In that case, we can put it out of the integral, and the work will be equal to f times s, which is just the area of this rectangle. So let's consider this example of a varying force where we have a force that is constant in direction but has a varying magnitude, so it is increasing linearly with x, okay? So the work done is just the area under the curve. So we want to find the work done for the displacement of 9 meters. So it is equal to the area of this triangle, which is half times 9 times the height, which is 4 newtons, which is equal to 18 joules. And another way is to do the integration, and we find f as a function of x. So we find the slope of this line, and then we integrate the equation, and we get also 18 joules. So thank you for watching. Please don't forget to like and subscribe, and see you in the next video.